Hi, Chuck McCown here. I've got another video for you today about a problem that has, I've become aware of it just recently, but it's been around forever. Just my own ignorance, and with the help of some of the people on the Animal Farm, afmug.com email list where all the experts hang out, they've educated me the error of my ways. Here's the issue. Got a lot of devices out in the world that put PoE, put power on Ethernet. And I'm talking about GIGE right here in this particular case. And this kind of represents the device. Maybe a router, maybe a switch, whatever. And so you plug it in. Now this is all 8 wires in the Cat5, so this is one port of a PoE switch, okay? And so you've got the data coming from, like say, the switch integrated circuit inside the device, and it comes out here and hits this transformer. As far as I know, all Ethernet products have a transformer coupling the +5 or +3 or whatever digital signals and so forth inside the switch. Actually, in the case of Ethernet, it's a lot more than just a simple digital signal. Coupling that through the transformer into a real-world impedance, line impedance of the Cat5 cable. Also provides what they call galvanic isolation, so impulses on the line don't get right into the chip, okay? Not nearly as easily as if it was directly connected. Electrostatic discharge resistance, lots of reason for using the Phi transformer. But in this case, these transformers on PoE circuits have a center tap on the secondary or on the output. And that's where you feed in the actual power, showing in this case, in this configuration, putting +48 on pins 1 and 2 and 4 and 5. And since it's fed into the center of the transformer, the current flows equally down both lines of the Cat5, and it doesn't cause any interference with the data. The data is circulating around in this circuit, and this power is traveling through the circuit as what's a common mode type of thing. I think I made a video that explained a lot of this. So, and then of course, you know, I've drawn, it actually goes into twisted pair and then Cat5. Sorry about the artwork here, but to a radio up on a roof somewhere. Here's the problem. A lot of you have bought my products and my line, or my surge suppression products to protect this piece of equipment and to protect this piece of equipment. Because what happens is you get a lightning strike a mile or two away. The voltage that's induced on the wires in this Cat5 cable is proportional to the length of the wire and the nearness of the strike. And I guess it would probably be proportional to the current of the strike too, because current and magnetism are directly proportional to each other. But we're talking, you know, 50,000, 100,000 amps. Slings out this big old pulse. It jumps on the cable. The cable, Cat5 cable, all 8 wires of it became basically a single winding transformer, air core transformer, where the lightning strike and the ionized air of the lightning strike is the one winding of the primary, and your Cat5 is the secondary of this nasty transformer. So it induces a huge voltage. You know, it can be, you know, as high as 10,000 volts, depending on the distance to the strike and the length of the cable that's exposed. So thankfully many people have purchased products to keep those impulses out of the equipment and direct them to ground. And so really all they do, you know, I'll just do this one right here. It just has devices in it that if the voltage gets too high, either from here to here or from here to ground, basically it's just a switch. It's a solid state device. Well, in my case, my products have both a solid state and a gas tube device. I don't even know what that would be called, a gas state. It's not a vacuum tube. And it sees a high impulse, it just shorts things to ground and bleeds off all of that juice until the surge goes away, and then it opens back up and waits for the next impulse. Well, see, here's the problem. This doesn't like that in some cases. This does not like to be shorted to ground. Some of these devices, if you short them to ground, you'll blow the whole port. Some of them, if you short them to ground, it just forces a reboot or reset of the whole switch. That's not good either. So it's surfaced that certain devices, you actually, the surge suppressor might save the radio, and it might save the rest of the ports, but it can blow a whole port, a surge suppressor, any surge suppressor, not just mine, any surge suppressor that does its job and suppresses surges and shunts them to ground. Any single one of those will wipe out a PoE device that doesn't like to be shorted out on its output. So typically these PoE devices can put out, you know, 1 to 2 amps aggregate total. Okay, so we're talking about all 8 wires. We're talking about 2 complete circuits. So if this device has a limit of say 2 amps total, and you've got these, this is the positive circuit here, and this is the negative circuit. So, or negative circuit. So you've got this round trip loop current that's 2 amps. So it's running on 4 wires here, and it's going out and it's coming back on 4 wires here. So you got 2 amps on 4 wires. There's 1 amp per pair. It's a half an amp per wire. Okay, half an amp per wire. Also, what do we do to limit it so that it's never more than half an amp per wire? Well, that's pretty easy. You have a really old-fashioned device. Has a symbol, looks like this. You got a fuse, a PoE fuse. Put that in line. Make it replaceable. How do you know if it's blown? Well, put some LEDs on it. So you could put an LED here. Have a hook to its corresponding return. And you put another LED here. Why would you have 2? Well, here's the deal. If you if the fuse blows and you've got power coming in, this LED will be lit. This LED will not be lit because the fuses have prevented the current from showing up on the other side over here. So if you have 2 fuses per pair, or 2 LEDs per pair, and both LEDs are lit, you know the fuse is not blown. If one of the LEDs is lit, you know the fuse is blown. If no LEDs are lit, you don't know what you got. You got maybe that's failed, maybe the power's out, maybe who knows what. It's impossible to really say if there's no LEDs, but chances are the fuses aren't blown. It's something else going on. So now the problem is, how big should you make the fuses? Well, one would think, okay, again, this is another one of those, one would think that a half-amp fuse would blow at like 0.55 amps. No, not so. It doesn't blow at 0.6 amps. It doesn't blow at 0.7 amps. I actually, in searching for fuses for this project, I called one of the main manufacturers of fuses, who shall remain nameless, and I had this week-long conversation with their engineers, applications engineers. I'm like, this is what I'm doing. I need a fuse that's going to blow at just slightly over half an amp. Which fuse is that? Well, tell us what your load impedance is. I'm like, I don't know. You got a lot of radios here out in the world. Well, what's your voltage going to be? Well, I don't know. These things can produce 24 volts. They can produce 48 volts. They've got a hard current limitation on them. I just want to make sure I have a hard current. Well, you got to tell us more design details. You know, what are you powering and what's your power source? Power source could be a variety of power sources. Loads could be a variety of loads. I've got one wire. I want to limit it to half a freaking amp. what one of your fuse products should I use? And it got more ridiculous over the period of the week. And finally, they just got frustrated. I mean, I got snarky. I'm like, I really am starting to regret the fact that I asked you guys what I presumed was a very simple question and is the primary question for your products. And they're like, we are done with you. Okay, fine. So what I did, design of experiments, started blowing fuses. I blew a lot of fuses. I heated up the mail with DigiKey fuse sizes going back and forth. I mean, coming in almost every day until I got it dialed in. On this particular manufacturer, if you buy a 0.375 amp fuse and you put 4 of them together here, okay, aggregate total will blow about 2.3 amps, something like that, 2.2 amps. And or I can use a 0.3 amp fuse and blow at 1.9 and change amps. So I thought, well, I want to make sure somebody buys a device that'll put out 2 amps. They can deliver 2 amps, even though it says 2 amps surge, I think it says 1.75 working. And my design may change, but what I'm going to show you here is the fruit of the labors and the proof of the product. All right, here's our setup. I'm going to power up this DC powered Ethernet switch. What I've got is I've got the switch coming out on the blue cable, running through the fuse product, and then going to, I've basically just combined all those 4 circuits together with hardwire and my Frankenstein switch here, and run these through an ammeter. To a power resistor, a really nice size power resistor. So there we are, folks. We're making power now. The switch is booted up. We're putting 53 volts out into the PoE. The switch itself is drawing 1.3 or 130 milliamps. And so now I'm going to, and you see I've got LEDs now. In this case, red and green. I mean, you can flip this around. In our case, green means the power coming in from the Ethernet switch, and current or power going out to the load, which in our case is a really nice hefty resistor. All right, so this resistor, I can slide this slider up and down here to get different amounts of resistance. Let's see where it's set. Right there, 1,875 milliamps or 1.8 milliamps. You see, we're over two on the power supply, but we're not over 2 on the PoE. So let me tap just with my probe here a little lower resistance and see if we can get over. Wow, I wasn't surprised. I was not expecting to see fireworks there. Okay, there you have it, 2 amps. Switch is not blowing. Let this run all day long. The resistor's getting hot. I can feel the heat coming off of here. So how high can we go before, well, what's going to blow first? Okay, that's the real question, isn't it? What's going to blow first, the fuse or the port? All right, this is the first time I've tried this because I really didn't want to blow ports on that thing, but this is designed to protect that. I'm going to give you something approximating, it's just loose so it can slide. Oh, that thing's warm. Wow. This is approximating our short. So keep your eye peeled on the current and the switch and the fuses and the LEDs, and I'm going to make it draw more current. I'm going to slide it down a little more, 2.1 amps. Slide it down a little more, 2.18 amps. 2.2 amps, 2.29 amps. Whoa! Well, I don't know if the camera picked it up, but check it out, man. 2.29, 2.3 amps basically. Fuse blew. Port did not blow. Port's still making all the voltage it's supposed to. And so I think I picked a pretty good spot for the fuse. You're going to get your fully rated 2 amps plus out of that thing. And you can rest assured that if the current goes too high, it's going to blow here before it blows there. I think I can make that assurance, okay? Now I could also, with the Franken switch here, just do a full-on short by just going like that. But you're just going to see an immediate blowing of the fuses. I've already done that part. So there you have it. Now the question is, all right, is that what we're going to get? Or are we going to get something like that if we buy this thing from you? Yeah, that's what you're going to get. I'm going to coat the top with conformal coating, but I want you to be able to see the LEDs. I'm going to paint the back, a good conformal coat. So there's not going to be any active circuits that are exposed here. Well, why don't you put it in a cute little plastic case, Chuck? Well, I'll tell you exactly why. It's economics, and this may change. The injection mold tooling to make a cute little case to snap over this thing is probably going to cost me close to $10,000. Now, if I'm only clearing $1 or $2 off of these things, you can see I got to sell quite a few of them to pay for that mold. And I'm not just willing to invest in that yet. It seems like, you know, I got to make 100 products like this for one to really take off good. If this takes off and I start selling, I mean, there's a lot of ports out there in the world, right? So I could be selling lots of these things. If it takes off and it looks like we've got growing trend in sales, yeah, I'll make you a cute little case to fit over it, and it'll still have little holes for the LEDs, and it'll drive up my cost by another, you know, 10 cents per unit, but amortize the cost of the tooling over, you know, however many units. It's not trivial. So anyhow, that's the end of the video. I enjoyed doing this project. I thought it was going to go a lot quicker because I really thought that the fuses, I thought the fuse guys could tell me is a little bit more about their fuses. Now, as it turns out, this is their derating curve, and at 125, I thought they might be real temperature sensitive. Nah, the rated current, it blows at pretty much 100% of its rated current until it gets up here and pretty hot. But even at scorching hot temperatures, which you'll never find, hopefully, in your knock, you know, hot temperatures hotter than what it takes to boil water, it's only at 95%. The current has dropped down. Here's the other crazy curve, though. This is their curves for, well, when's this 375 milliamp fuse going to blow, okay? So what we've got here is a scale across the bottom in amps, right? It's a logarithmic scale, and this is how many seconds you've let it run. Well, I've let them run a lot more than 10,000 seconds over here on the side. But let's say 10,000 seconds. You draw this line down here, and that's, oh, I missed it. Let's see, having a hard time tracing it. 0.4, 0.5 amps. 0.5 amps for a 375 milliamp. Well, guess what? It really does blow about 0.5 amps. So what does their number really mean? I guess the only thing you can take away from this is that a 0.375 amp fuse can be put in a 0.375 amp circuit and have 0.375 amps on it forever, and it's never going to blow. It doesn't tell you when it's going to blow. So anyhow, ciao.